Hi, guys. How you guys doing?
Good. How are you?
Good. You know, all things considered. All right. Let me just make sure this is all in. How are things in Boston this morning? I'm just outside of Boston.
Pretty good.
A nice day out anyway. All right. We'll give it a minute for other folks to show up. Actually, this was just my note to myself. Wanted to call you guys' attention to a switch over in our syllabus that's coming up upon us in the next week or so. So we are switching books, right? On our syllabus, it says we're going to do chapter 4.1 next week, 4.2 next week, but 4.2 is actually chapter 1.1 of our integral calculus book. Okay, so we're going to start calling it chapter 1.1 and chapter 1.2, whatever. When you see those in the latter half of our syllabus, right, and like our homework assignments, it'll say chapter 1 homework. It's not our textbook going back to our textbook from the beginning, right? The differential calculus book. It's the next book that we're working with. Okay. Now remember, this class is one of a sequence of classes. We've got Calc 1, 2, and 3. Right, Calc 1 and 2, where we start to cover Calc 2 at the end of this class, which is we're getting into now, like next week, essentially, we're moving into Calculus 2 topics. So keep that in mind. If you haven't gotten the next book, which is the Integral Calculus book, make sure that you get it. You'll need it also for next semester, which is a Calculus 2 semester, which also, by the way, I am teaching Calculus 2 next semester. If you want to register for my class, I'd be happy to have you as students again next semester. Obviously you're free to register for whatever class you want that fits with your schedule, but just to let you know. So keep that in mind. We're going to start calling it chapter 1 in the next week or so, but it's not our chapter 1 that we already covered. Differential, it's integral calculus. Okay, so that's something to keep in mind. I also want to talk for a few minutes about our quiz. You'll notice I graded the quiz that you guys took last week. I put up the grades yesterday, and I'm going to scan in the solution set today and then post it later today, so you guys will have it. I wanted to talk about the quiz because I noticed there were a bunch of you in this class as well as in my 8 o'clock class who had the same wrong answer on on question 2, say question 4. Some of these are complex derivatives that they're like functions composed of other functions. And I checked Wolfram Alpha, which is one of the many online calculus solution solver programs, and the answers looked almost identical to what Wolfram Alpha had there. Wolfram Alpha can often be wrong. They're using different techniques, some of which don't really apply, or sometimes it transcribes the problem incorrectly and doesn't do it correctly. It looks like in some of the solutions that we did for this quiz for the derivatives that it was using maybe a Taylor series expansion to do the derivative, which is something that, first off, we haven't learned. Taylor series, it's an approximation of the function. Okay, so you're not even taking the derivative of the function itself. So be very careful. I know it's going to seem like, you'll want to check these things to see if you did it right. It's a quiz, it's worth a lot. You're better off actually getting that problem wrong and dropping this quiz as a quiz grade, and then coming to see me and we'll talk about how do you actually get it right. These quizzes are set up to, just to kind of see if you understand the material. We're not trying to fail anybody. So we're not trying to trip you up on any of this stuff. But I want to talk about the solutions for how we actually do some of these problems, because I noticed, like I said, the same wrong answer. On a lot of these, U substitution is going to be your best bet for these complex derivatives. So if I have h of x is equal to the cosine of the inverse tangent of x squared, right? This is the one that I saw in particular had a lot of Wolfram Alpha type answers that were incorrect. You lost points. I didn't take off full points on it, but I did pick off points. But here, right, it's going to help if we do a u substitution. So if I go u equals my inverse tangent of x squared, right? This is actually a composed function of its own, so I could even do another substitution on here too. I'm just gonna have to remember to do my chain rule. When I take the derivative of my inverse tangent, it's 1 over x squared. So it would be squared. So this is gonna be x squared squared. And then don't forget, we have to do a chain rule derivative of what's inside. So this is gonna be 2x, right? So now this is my u, this is my du. I can rewrite this as h of u equals the cosine of u, right? Much more simple, okay? So now when I go to take the derivative, in terms of u, I'm going to get minus the sine of u times du. Pretty straightforward. Now I have to substitute back, right? And don't forget, we're going to rewrite this as h prime of x. Okay, because we're switching our variables here. So I'm going to substitute back. So minus the sine. We said our u was inverse tangent of x squared times du. This is going to be 2x all over 1 plus x squared. Squared is x to the 4th. Okay, you can put this all together. Minus 2x, 1 plus x to the 4th times the sine of the inverse tangent. Okay, and that's your derivative. It's pretty straightforward if you do the u substitution. If you did it like Wolfram alpha, they had you do some kind of a weird polynomial substitution here. You're taking all sorts of derivatives. Like I said, I think they were doing a Taylor series expansion on it, which is something, first off, we haven't learned yet. Second off, it's an approximation. Okay, so we're looking for our actual derivative. And it's also possible that Wolfram did it wrong. Okay, you'll see that also when you do calculus 2, it's going to evaluate certain integrals and do certain things, and it's going to be incorrect because technically it's following through stuff, but it's not processing it correctly. Okay, so be very careful. Those online solution solver programs are not always your best bet. Question 3 is the product rule. That's pretty straightforward. Question 4 is another one that I saw with it looked like maybe some kind of an online solution solver was for 2. So we have g of t equals the inverse sine of log base 5 of t, right? So I said u equals log base 5 of t. So when I typed this into Wolfram alpha, I wanted to see what would happen. What it told me on Wolfram alpha was that this was the natural log of 5 times t, which is incorrect. Okay, incorrect. Right, so even Wolfram alpha couldn't resolve what this was. So when I saw this in some of the answers, I knew that people had been relying on an online solution solver. You know, we're kind of, you know, using our honor system here on these things because we're doing things remotely. So, you know, I'm going to trust you. I'm not taking off points for looking things up online. I'm going to trust you guys that you're not. I'm telling you also that the online problem solvers are going to be doing things wrong. So just think for yourself and then think about what you need to do. So I have log base 5. So when I go to take the derivative of a log other than like natural log or log base 10 or whatever, I'm going to be thinking, remember we did this in chapter 1, change of base formula, right? So the first off, my change of base formula says log base 5 of t is the natural log of t all over the natural log of 5. Natural log of 5 is just a number, right? And I can plug that into my calculator right now and get out a number. So I'm going to go natural log of 5 is just a number, right? So you could plug in that 1 over 1.6094, or you just leave it as 1 over ln of 5. But this looks like 1 over ln of 5 times ln of t. And I'm writing it this way because this is a number times my variable, right? So when I go to take my derivative, so if I say my u equals this, then my du, right? I've got my coefficient 1 over ln of 5, that's just a number, times 1 over t, right? So this is what we're dealing with. So here's my u, here's my du. Now I can do my substitution of variables. So g of u equals inverse sine of u. Not so bad, right? So now when I go to do my g prime, right? Remember your inverse sine derivative, right? It's 1 over 1 minus x squared in a square root. So I've got 1 over u squared square rooted times du. Okay. Now I get to substitute back in for u and du. Okay, don't forget to change that variable too. I'm going to use this u in here, and I'll use this du over there. Just so g prime of t equals 1 over 1 minus log base 5 of t squared rooted times du 1 over ln of 5 times 1 over t. Remember, this is just a number. I could have used this 1 over ln of 5 times ln of t as my squared term. Either way is fine, right? I just kept it simple like this. Okay, and then this is what I'm dealing with here. And I can leave it like that. So be very careful. Like I said, when I checked this on Wolfram Alpha, I saw some of the answers that I saw in your quizzes, and it was wrong. Okay, so like I said, I didn't take off points because I can't prove that you guys did that, but I'm also telling you that it gave you the wrong answer. So be very careful about using those online solution solver programs. It's going to be tempting, right? Because you're going to want to see if just check your answer really quick, but you're not going to know. I mean, maybe it's doing it incorrectly, which they often do. So be very careful, okay? I've got my solution set for this here. I'm going to scan it in, and I'll post it up online so you guys can have that to study for our final exam, okay? Okay, all right, so enough about the quiz. Do you guys have any questions you'd like to ask about homework? Remember, we have chapter 3.3 and appendix A that are due tomorrow night, and those are the basis for our quiz tomorrow that starts tomorrow. And you can put it into the chat if you want, or you can just ask me. We'll have some time tomorrow too if you want to ask questions tomorrow about it. 3.3 number 19. 3.3, 18, 19. Yeah, this is a nice one. All right. Chapter 3.3, question 19. All right, so we're given, I'm going to draw here. Here's our radius. Let's do this. Here's our okay, so then what we want is what is the maximum area of the rectangle? And then our diagonal is equal to our diameter. Okay, so that's an important clue, that our diagonal is equal to our diameter. So let's write down what we know. The area of our rectangle is equal to base times height, width times height. So b times a gives us the area of our rectangle. The area of the circle is equal to pi times r squared. So this is our r squared, okay, which I can also think of as pi times 1/2 d. Oops, sorry, I wrote that wrong. Getting ahead of myself here. 1/2 the diameter squared, right? So the diameter, cut it in half, get my radius. So I'm gonna just getting things in terms of like, d, right? So now if I think about my area in terms of my diagonal, right? So it's a rectangle, so it has a right angle in it, which means I can use the Pythagorean theorem. So I'm gonna go a squared plus b squared equals d squared, but I'm gonna take the square root of both sides. Okay, so a squared plus b squared equals square rooted equals d, right? Using our Pythagorean theorem, because this is a also here, right? Which is equal to 2 times our radius. Okay, so that means that I can say a squared plus b squared equals, if I square this whole thing, I'm going to get 4 radius squared. Okay, so I'm going to solve this in terms of a. So a equals our 4 radius squared minus b squared square rooted. Okay, my whole point is to try to get this in terms of one variable or another. Area of the rectangle as a function of a and b equals a times b. So my area of the rectangle as a function of b equals, right? So I'm going to substitute in, right? I just solved for a, so I'm going to plug that into here, right? So what this value is, I'm going to plug it into there. So I'm going to get 4r squared minus b squared square rooted times b, right? So I plug that in for my a value, so I get my area for my rectangle. Now I can take the derivative, set it equal to 0, right? This is going to give me, this is 4r squared minus b squared raised to the 1/2 power. So I'm going to do my power rule on it, right? So, but I've got this, right? I'm going to have to do the product rule because this is as a function of b. So I need to do the product rule, right? So I'm going to go first 4r squared minus b squared to the 1/2 times the derivative of the second. And then plus the second times the derivative of the first. This is going to be 1/2, sorry, 4r squared minus b squared to the minus 1/2. And I have to take the derivative of what's on the inside, but I'm doing this with respect to b. So this becomes minus 2 times b. Okay, chain rule, right? So now I set that equal to 0 and I solve for b. So I'm going to get, let's make it look nice. This is going to be 4r squared minus b squared 1/2 minus b squared all over 4r squared minus b squared to the 1/2, which basically, and this is equal to 0. So I, move it over, and then like I bring this to the other side. I, make everything positive, and then I can multiply both sides by that. So basically, there's some algebra in here that I'm skipping. So I'm getting 4r squared minus b squared equals b squared. Some algebra, and we get to here, right? So then I'm going to add, right? So then I'm going to get 4r squared equals 2b squared. Then I'm going to get 2r squared equals b squared, and I take the square root. So I'm going to get b equals radical 2 times r. And I'm only taking the positive aspect of it because having a negative b doesn't make sense, right? So this gives me b. I plug it back in to solve for a. So a equals 4r squared minus b squared square rooted, which is equal to 4r squared minus radical 2 times r squared square rooted. Is going to give me 4r squared minus 2r squared. Is going to be equal to radical 2 times r, which is equal to a. Does it mean it makes sense that we're basically dealing with a square, right? So, oops. Right, so I did a, you didn't see it, but I did a first derivative test. First derivative test, right? So our first derivative changes sign from positive to negative at b equals radical 2r, which means that that this b equals radical 2r is a max, right? Which is what we wanted, right? So basically, right, a and b equal to each other, so we're dealing with a square, right? So we basically don't have an ellipse. Like when they said, once they said, like if we had a rectangle, if this was truly a rectangle, then we're dealing with an ellipse, right? Okay, but then once we said that this, radius here, that this was a diameter, right? If this is a diameter, then I know it's got to be a square, but that's okay. We have to prove it, okay? So the a equals b, right? For it to be a square. If a didn't equal b, sorry, you can see that if it didn't equal b, then we'd be dealing with an ellipse. Okay, so we have a square. Okay. Whew, a lot of stuff. Okay. Great. 42, question 42. Yeah, let's see, 42 is a long one. Let's we can go through 42 also. This is chapter 3.3, question 42. All right, so I'm kind of, usually I post these things online, but because we have today and tomorrow to cover chapter 3.5, I can spend a little bit more time actually talking through the details of these problems here. So let's draw out our picture. I've got this here. So this is 30 feet. I've got my water line. Junction happens here. So this is 30. This is a right angle. I'm just rewriting this here. This here to here is 40 feet. This one here to here. This value right here is X. And then so here's our water line, here's our hydrant, right? And we're trying to look at like, where do we put this, right? So this line here, let me write it like this. This is 40 minus X, right? Because this is 40, this is X. So this piece here, from here to here is 40 minus X. This here is 30. So with the Pythagorean theorem, with the Pythagorean rule, I can a squared plus b squared equals c squared. I'm going to write this out like this. This is going to look like 40 minus x squared plus 30 squared. Okay, so that's this side right here. Okay, so that's that side. So we're dealing with, we're using our Pythagorean theorem to help us come up with things. You just draw a picture. It's going to help you, think it through, like, what are the sides of my triangles and how do I think this through? So, so we have 3 extreme piecewise paths for our pipeline. Okay, so we've got the longest and shortest, right, that we need to think about. So what I'll do, I'll draw some of these out. So I can go 30 feet and then 40 feet, right? Or we can go 40 feet and then 30 feet, right? Or we can go 30. This is going to be, it's actually 40. And this here, let's draw this out. So this triangle is going to look like 30 squared plus 40 squared, square rooted. Okay, so we've got these different shapes. So this is like our extreme, right, pieces. All right, so now our cost, we were given different costs for things for part B. So we were told this is $40 per foot if we go under the street, right? And it's going to be $20 per foot if we go under the ground. This is assuming this is where the pipe goes. Right, so it's like this, 30 to 40, like that, right? All right, so now go ahead and think about it. So I'm going to go like this. So 40 feet times 20 feet plus 30 feet. Oh, sorry, $20 per foot. And then this is going to be $40 per foot. Which gives us a max of 2,000, right? If I do these maximums. That's going to be the same as if I went 40 to 30, like this, right? So it's good. So B and C are going to be the same cost, right? So then D says, what's the minimum cost of pipe? So our maximum, right, is if I use the legs of the triangle, right? So the minimum is going to be if I can exploit this distance here somehow, like find what's the optimal, what's the optimized way of doing that, right? So then our cost is going to be X times 20 plus 40 minus X squared plus 30 squared square rooted times 40. So, right, so we're going this distance, okay, at $40 per foot because we're going under the street, and we're going this distance under the ground at $20 per foot. So that's what this means. I'm going this distance, sorry, this distance times $20 per foot, my hypotenuse of my triangle times $40 per foot. Okay, so this is, I have to take the derivative, right? With respect to x is the function of x. I have to take the derivative with respect to x, and that's going to give me 20, right? Because this is x is my variable. Plus, now I have to do all of these, this is the power rule. So 1/2, 40 minus x squared plus 30 squared to the minus 1/2. Now I have to do chain rule 2, right? I have to do this part here, 40 minus x raised to the 1, and then I have to do chain rule times a minus 1. And then this is all multiplied by 40. Set it equal to 0 is a lot of algebra. Set it equal to 0, we're going to solve for x. So there's some algebra here. So this is minus 40. I'll show you a little bit. Okay, so there's some algebra, right? And then I get to here. Okay, so I find that my x is 22.679. I need to know that's going to be a minimum. So test on C1 of x, right? We find that it changes sign from negative to positive. Right, which is what we need to prove it, right? And oh, we're told x is between 0 and 40. That's our max, right? So so if I do C of 22.679, I'm going to get 1839.23, and then C at when x is equal to 0. This is a straight line pipe. Right, when x is equal to 0. So this is, we said was 2000. We did this before. And then same thing for 40. This is totally indirect. This is the legs of our triangle. We get also 2000. Okay, so this one is cheaper. Right, so that's it minimizes our cost, which is what we want. We want to minimize the cost. I'll post the videos later today. So in case you didn't capture all the stuff that I just wrote, you'll have it in the video. You can pause it and then see, you know, how I did it. Okay. We'll do the last one, 21. Then we got to move on to chapter 3.5. All right, so. Okay. You guys all set with that? All right. Question 21. So we have 100 meters of fencing. Okay, we want to do a rectangular enclosure against a wall. This reminds me of like some standardized test questions that I remember taking. We had this. So we've got our wall. And then we're going to do our fence. Right, so the fence has a width and a height. Right, so here's our fence, here's our wall, so width and height. So I've got this whole thing is 100 meters, right? So what's the largest area of the enclosure? What are the dimensions of the enclosure in A? So I want to maximize our area. Right, so our area is going to be width times height. So that's going to be, I need to think about what's going on. So my width is going to be, before I write this down, let's take a little note over here. So our perimeter, right, is 100. we've got this wall, so I've got 100 that goes on only 3 sides, not on all 2 sides. So I've got a W plus H plus W, right? So I've got 2 W's and an H. Okay, so if I solve for H, I'm going to get H equals 100 minus 2 times W. Okay, based on the dimensions that they gave me from the start. So I'm going to substitute, I'll get all this in terms of my W. So 100 minus 2 times W is my area. Okay. Let me write this down again over here. So my area as a function of W is equal to W times 100 minus, which I'll write out 100W minus 2W squared. Okay, so now we're optimizing. So I've got to take the derivative, right? You want to get this in terms of one variable or the other so that, you know, when you take the derivative, you know which variable you're working on. So this is going to become 100 minus 2W. I'm sorry, not 2W, 2W times 2. 4W. 4W. Okay, and I set that equal to 0 and I solve for W. So W equals 25. Okay, and that makes my H, right, 100 minus 2 times 25, which is a 50. This is meters. Okay. Now I need to do a check to be able to tell. I have to do a check to see if I've optimized it. Check to optimize. If you don't do the check, you won't get full credit. So I'll do the second derivative test. Oops. Second derivative. Because taking the second derivative is pretty easy. It's going to be easier to do the second derivative than it is to do our first derivative test. But it's up to you. You can do first derivative or second derivative test. So I'm just going to get a minus 4. Minus on my second derivative means it's concave down, right? Which puts this at a max, right? So, I mean, my second derivative is negative no matter what my W is. So we know that this is going to be a max value, okay? So now our area, right? So if I plug it in, my area is going to be 25 times 50, which is 1,250 square meters. Okay. And then B, they wanted to know the dimensions. We've got the wall. I'm going to go out 25. I'm going to go down 50. I'm going to go back 25. There. Okay. Fun stuff, right? Like I said, this reminds me of standardized test questions. Okay. Okay. Whew. All right, let's go ahead and get started on chapter 3.5. Very exciting stuff. Chapter 3.5. Okay, chapter 3.5 is LHopitals Rule. And we need to talk about indeterminate forms. Can't do LHopitals Rule without talking about indeterminate forms. So let's take a step back for a moment and then talk about what is an indeterminate form. Okay, so if I'm taking the limit as x goes to some value, whatever, x goes to a, and I've got, you know, a rational function, f of x over g of x, and I evaluate this at x equals a, right? And I get my limit is equal to 0 over 0. All right, well, I know what to do if it's 0 over some number, 0 over 5. And I know what to do if I get some number over 0, right? But what do I do if I get 0 over 0? What's my answer going to be? Is it 0 or is it not defined? You find yourself scratching your head and wondering which one is it going to be. You're dealing with an indeterminate form. You can also have a case where I've got something like infinity over infinity. Okay, so when I take the limit as x goes to a, f of x goes to infinity, g of x also goes to infinity. The question is, if I have infinity over a number, then my limit is not defined because it's unbounded. If I have some number over infinity, my limit is equal to 0 because I have a ginormous number dividing into a much smaller number. It makes me go to 0. But if I have an infinity over infinity, the question is which one gets there first, right? If you're scratching your head wondering which one it's going to be, that's indeterminate. It's also possible I could have 0 times infinity or infinity minus infinity, right? These are all examples. We're going to talk a little bit more tomorrow. We'll talk more about other types of indeterminate forms. But if you find yourself asking which term dominates, the 0 or the infinity, or the, is this a 0 or is it infinity? What's it going to be? If you find yourself wondering, okay, that means you're probably in an indeterminate form, which means you can use L'Hopital's rule to help you process that indeterminate form and help you evaluate this limit here. Why do we care? We care because, right, we're often dealing with situations where we have some complex function, usually some kind of rational function, as it approaches some value that we want to know what's happening, right? It's approaching some value. As it's approaching some value, I need to know what this function is doing. What's the behavior of this function, right? I need a way to be able to process it. And I have to be able to evaluate which function gets to that point before the other one does. This is actually common in computer algorithms. I need to be able to process, like, say, search algorithms. One of them has a search capacity that's modeled by this function. One has a search capacity modeled by that function. Which one's quicker? Okay, so I need to know which one's going to get there first. So L'Hopital's rule helps us with that. It's a theorem. And I can only use L'Hopital's rule when I have an indeterminate form. We're going to see later, if I do L'Hopital's rule on something that doesn't have an indeterminate form, I get the wrong answer. So be very careful. Don't just think, I'm just going to do L'Hopital's. That's great. You got to make sure first, check it to make sure that it's indeterminate, and then you can do L'Hopital's. Okay. Alrighty. So let's write down what L'Hopital's rule is. Then we'll start playing around with it. All right. So first off, I'm going to assume that my functions f of x and g of x are differentiable on an open interval containing a, x equals a, right? So f of x and g of x, I can take the derivatives on some interval, some open interval. Interval can be whatever we've decided it to be. That interval is going to contain that a value. This is our limit goes to a. So a is on that interval that we're looking at. And then we're going to deal with this first indeterminate form, the 0 over 0. And f of a equals g of a, which is equal to 0. Okay. Also, we want to assume that our derivative of our denominator function does not equal to 0, except possibly at x equals a, right? We want to leave that open because that's part of our indeterminate form that we're dealing with. Okay, so let's talk about our L'Hopital's, right? So if I take the limit as x goes to a, f of x over g of x, right? And I get an indeterminate form. Right. Initially, we were talking if it's 0 over 0, but this is true for these other indeterminate form types. So what I can do is I can take the limit again as x goes to the same value of, I take the derivative of the top divided by the derivative of the bottom. I'm going to write this in red, super, super careful. This is not quotient rule, not quotient rule. I'm just raw, taking the derivative of the top, take the derivative of the bottom, and I evaluate my limit. This is what you want your quotient rule to be because it's easier, right? I don't have to worry about bottom, derivative, top, whatever. It's just derivative over derivative. The reason we do this is because there's, like we've been studying all semester, a relationship between our function and its derivative, right? We can use our derivatives to describe the nature of our function at this particular point. That's what we've been doing all along, right? So like at this particular point, my function's increasing or it's decreasing or whatever. So we're exploiting that property to help us evaluate if our limit gets us into an indeterminate form. Okay, so this is also true if f of x and g of x are differentiable near a, but not equal to a. That's all that's saying is, like, remember our behavior of our function as we're approaching some value, right? So this L'Hopital's rule will also be true if as our function approaches some value, it's equal to, if it's near that value but not equal to it. And the limit as x goes to a, f of x equals plus or minus infinity, and the limit as x goes to a of g of x equals plus or minus infinity. So again, we're dealing with other types of indeterminate forms, right? Infinity over infinity, minus infinity over minus infinity, things like that, right? This is also true for one-sided limits. Okay, right, so some functions aren't defined, right? Our natural log isn't defined for values of x less than or equal to 0. So I only have a right-sided limit as x approaches 0 from the right. I need to be able to evaluate my function. L'Hopital's will also work for one-sided limits. Okay. All right. So I've got my lecture examples. I printed them out. There's a typo. It says 3.3. It's really 3.5. You'll see it. The file itself is called 3.5, but I accidentally called it 3.3 on the inside. You might want to change that. All right. So we're going to use L'Hopital's rule to evaluate this. I'm telling you ahead of time to use it, but let's just do our quick check. Check to see if indeterminate. I have to check first because so I need to evaluate the limit, right? Before I even jump in and do L'Hopital's, I'm telling you to do L'Hopital's, but before you even jump in and do L'Hopital's, check to see if it's indeterminate. So that means as x goes to 2, let's plug it in. This is going to be 2 cubed minus 8 all over 2 to the 4th plus 2 times 2 minus 20. So 2 cubed is 8. 8 minus 8 is 0. 2 to the 4th is 16 plus 4, 20 minus 20. 20 minus 20 is 0. So it's indeterminate, which means it's a candidate for L'Hopital's rule. I'm going to do L'Hopital's, right? So at x equals 2. So it's the same limit. Limit as x goes to 2. I take the derivative of the top. 3x squared minus 0. 3x squared all over. Take the derivative of the bottom. 4x cubed plus 2. Now I get to evaluate it again. So let's try it again. So 3 times 2 squared all over 4 times 2 cubed plus 2. Parentheses. All right, so this is 2 squared is 4 times 3 is 12. This is 2 cubed is 8 times 4, 32 plus 2 is 34. So I can leave it like that, or I can simplify it, 6 over 17. Okay. Try this one. Okay, so I'm first going to check. So I'm going to plug this in. So 4 minus 2 squared all over the sine of pi times 2. So 4 minus 4 is 0. Sine of 2 pi, let's remember, 2 pi, I've gone full circle. 2 pi is the same thing as 0. The sine of 0 is equal to 0. So it's indeterminate, which means I can use L'Hopital's. Okay, so I'm going to do L'Hopital's again. So limit as x goes to 2. I take the derivative of the top minus 2x. Take the derivative of the bottom. Don't forget your chain rule. I've got a pi. Derivative of sine is cosine pi x. Let's try it again. I'm going to evaluate. So minus 2 times 2. Already, I know I'm not an indeterminate form. Look, I'm going to get a minus 4 in my numerator, right? So already, no matter what I get in the denominator, I'm not indeterminate anymore. Pi, so cosine of 2 times pi. So pi, cosine of 2 pi. Let's think. Full circle, cosine of 2 pi, right? It's the same thing as cosine of 0. Cosine of 0, remember a unit circle, that's equal to 1. So this is pi. minus 4 over pi. Okay. All right, let's try this last one here. Let's try it. So I'm going to do a quick check. So cosine of pi over 2 squared, right? So cosine squared, I can write it like this. Cosine of pi over 2 quantity squared all over 1 minus the sine pi over 2. Pi over 2, that's right on my y-axis. That means my cosine of pi over 2 is equal to 0. 0 squared is 0. So sine of pi over 2, sine of pi over 2 is 1. 1 minus 1 is equal to 0. So it's indeterminate. So I'm going to do L'Hopital's again. I know it looks funny. I'm writing this, kind of the habit of writing it. Calc 1, Calc 2, we need to tell people we're going to do L'Hopital's rule. As you move on into Calc 3 and your other math and engineering classes, you don't have to state that you're doing L'Hopital's rule. You can just do it. We need to see that you know what to do. So for Calc 1 and Calc 2, you need to tell us that you're doing L'Hopital's rule, or you risk losing points for not showing your work. Seems unfair, but as we're teaching you these things, we need to know that you're applying it correctly. All right, so let's take this derivative. So I'm going to rewrite this. This is cosine of x quantity squared. So when I take that derivative, I'm going to do the power rule. So that's 2 times the cosine of x times my chain rule minus the sine of x. All over my derivative on the inside, the 1 becomes a 0. So minus, so this is cosine of x. So this is the limit as x goes to pi over 2 to cosine of x times sine of x. I'll cancel out the negative all over cosine of x. Okay. All right, so now I have a removable discontinuity. This is technically still 0 over 0, right? Because it's still indeterminate. Removable discontinuity. So still indeterminate at pi over 2, but due to removable discontinuity, we can evaluate the limit. Okay, so that's basically going to give us the limit. This x goes to pi over 2 of 2 times the sine of x. Sine of pi over 2 is equal to 1. 2 times 1 is equal to 2. Okay. My removable discontinuity allows me to do that. It's still indeterminate, but I have a way to evaluate it, right? Just like these functions are still indeterminate, but I'm using L'Hopital's rule to help me evaluate it. Okay. You guys all set with that? All right, let's take a look at example number 4. So this is an interesting one, right? So first off, I have a one-sided limit, right? Which, oops, sorry, you can't see what I'm writing. This is a one-sided limit, which we said before, L'Hopital's rule applies to one-sided limits, right? But I've got a term times a term. So it's not in a term divided by a term. So I need to rewrite it so that I can get it into a form that I can use L'Hopital's for. But let's just take a look. Why do I care? Why can't I just plug this in and say, well, it's 0 times ln of x, so it's equal to 0. Well, this is the big question. So as x goes to 0, right, from the right-hand side. So let's take a look. I'm going to graph it out. Here's my x-axis. As x is going to 0 from the right-hand side, right, my function x, this function here, function number 1, x equals 0, right? That goes to 0. As x goes to 0, my ln of x goes to minus infinity, right? My ln of x function goes like this. We have an asymptote here, so we're never going to be able to evaluate this exactly. That's why we say it's approaching it from the right-hand side. So the question is, which one gets there first? Which function, x or ln of x, gets to destination first? This is a big question in computer search algorithms, right? Like, is it going to get to 0 first? That means that my x term dominates. That means my limit's equal to 0. If the ln of x term gets to minus infinity first, then that term dominates and the limit's equal to minus infinity. So we're really dealing with a 0 times infinity situation. So 0 times infinity is also indeterminate, right? Because when I'm asking myself that question, which one works, that's indeterminate. So I have to rewrite it into a L'Hopital format, which means a function over a function. So I'm going to say the limit as x goes to 0 from the right-hand side of ln of x all over x to the minus 1. I didn't change the function. I just rewrote it. Remember, we always said if it has a negative exponent, it belongs on the other side of that dividing line, right? So this 1 over x to the minus 1 is the same thing as x to the 1. All right, well, it also means because it's indeterminate, so this is infinity over 0, which is indeterminate, right? So basically I can do L'Hopital's. Okay, so I'm going to go limit as x goes to 0 from the right. ln of x, I take that derivative, I get 1 over x. X to the minus 1, if I take that derivative, I get minus x to the minus 2. Okay, so this is, let's do some algebra. I'm going to get x to the minus 1 all over minus x to the minus 2. This is equal to, right here, so equal to the limit as x goes to 0. This is equal to minus 1 over x to the minus 1, which is equal to minus, let me write it out here. 0, this is equal to minus x to the 1, okay? Which is equal to 0. 0 times minus 1 is 0. So what that means is that my x term dominates. My x term gets there first, right? So this is saying that the x term gets to 0 before the ln of x term gets to minus infinity. So L'Hopital's help us evaluate that. It's super important. I need to know that, right? Because I'm often, you're often in life, right, as you're modeling situations, going to be getting complex functions like this. And I'm going to be looking at values. I need to know as I approach some value, which of these terms is going to dominate, which is going to get there first. It's a race. Does x get to 0 or does ln of x get to minus infinity? L'Hopital's is going to help me evaluate that. Okay. All right, let's do this one. I'll tell you ahead of time, we're going to use L'Hopital's twice. I'll give you a hint. We'll finish with this example and then we'll pick up 3.5 tomorrow. And then I can also answer, if we have time at the end of class tomorrow, I'll answer other questions for 3.3. So let's just do a quick check to see if this is indeterminate. So I'm going to go limit as x goes to 0. So e to the 0 minus 1 all over cosine of 0 minus 1. So let's take a look. This is 1 minus 1, that's a 0. Cosine of 0 is 1, 1 minus 1 is 0. So that's indeterminate. Okay, so I need to use L'Hopital's. Okay. So you use L'Hopital's. So I'm going to say the limit, repeat my limit. So I take the derivative of the top. Derivative of e to the x is e to the x. Derivative of minus x is minus 1. Cosine minus the sine of x. Right, the minus 1 term goes away. All right, so now I'm going to reevaluate this. So this is going to be e to the 0 minus 1 all over minus the sine of 0. So this is 1 minus 1. This is 0 all over 0. Still indeterminate. I can keep going, take in as many derivatives as I need to. I take it again. So the limit as x goes to 0, I'm taking this derivative here. So this is going to be e to the x now, because that derivative is 0, minus the sine. So minus times sine of x. So if I go to evaluate, this is going to be e to the 0 all over minus the cosine of 0. So e to the 0 is 1. cosine of 0 is 1 times the negative, so this becomes -1. Okay. We did L'Hopitals twice in order to help us with that. And what I'll do is I'll end here so that we'll have time to pick up and talk about things tomorrow. And on the same chapter, we'll continue with 3.5 tomorrow. Like I said, you guys don't forget to, this stuff is due 3.3, Appendix A is due tomorrow night. That's what our quiz is based on. And then if you haven't already purchased the second calculus book, you're going to need it because we're going to start doing problems and stuff from the second calculus book when we start in on chapter 4. 4.2 is actually chapter 1 in the integral calculus book. Okay. Have a great day, guys. Take it easy.
you.
Thank you.
Bye.
Have a good day.
Thank you.
Take care.